right. Hello, everybody. Welcome to our next installment of remote learning here. Actually, this will be the last video of new stuff. Next week, I'm gonna send out some kind of practice test, full-blown practice test. Likely will, it's not going to be one of those short 6-question ones that I've been doing on AP Classroom. It won't be anything except a full AP practice test, just a bunch of practice AP problems to try and get us ready for that test. One other thing I want to mention is that I'm going to be putting out a survey on Google Classroom about telling me what times are going to be either work for you or what times are not going to work for you. Because I want to set up some kind of Zoom review or Google Meet review. I know I haven't been able to do any of those so far, and being able to ask some questions that way I think is pretty important, and I know that. So I want to make sure that at least one time we get something like that set up, so I can be a resource for you. You can get on there and ask me some questions, and we can get ready for that AP test. Okay, so last lesson here is angular momentum, finishing up all of our circular motion stuff right here. Okay, so what I want to do is compare angular and regular momentum, kind of like I have been doing for the last couple videos here, comparing things we've done already to the new circular stuff, which really isn't that new, just new symbols, and that it's going to be the same kind of vibe here. So when we did our momentum unit, we had the equation P equals mv. So the momentum is just equal to mass times velocity. If you do mass times velocity, then you've got momentum. Okay, so rotational momentum is going to look like a very similar equation. Okay, L equals I omega. Kind of like how last week, instead of an M, we saw the I. It's the same switch from M to I. M is mass, I is moment of inertia. And we're seeing the same switch with the velocity. We're changing from regular velocity to circular velocity or rotational velocity, and that's omega. So for rotational momentum, L equals I omega, or moment of inertia, times angular velocity. L is our symbol or variable for angular momentum. So instead of P, we've got L. L is still momentum, just like P is, just going around in a circle instead of going in a straight line. That's all. When we talked about the momentum unit, we also talked about impulse, which is just a change in momentum. So if your momentum goes from 10 to 30, that means your impulse was 20, because that's how much to go from 10 to 30, how much do you have to go up? You have to go up 20. So that would be your impulse. Okay, so that we're also going to be talking about that here as well. When we did this the first time, it was delta P equals Ft. So your change in momentum is equal to force times time. Force times time, that tells you how much your momentum changes. It's going to look very similar for rotational impulse, just with all of our regular variables turning into their circular versions. So just like over here, P changed into L, still momentum, just P is regular momentum, L is momentum in a circle. Force, instead of force, we have torque. Remember, though, what is torque? Torque is a force that makes something that moves in a circle. The only difference between force and torque is that is the radius, how far you are from the center, that matters. And then T is still the same T, though. T is time. That's nice. It didn't change. So we just have L instead of P, still momentum, just in a circle, and we have torque instead of force. Remember, all these arrows mean that all of these things are vectors, so direction matters, but really doesn't seem like I haven't seen any homework. I don't think any of your homework problems really dealt with anything that changes direction, so we've pretty much been able to keep everything positive, which is kind of nice. We learned that in the momentum unit, we learned that when a force is applied to an object, it changes the momentum of that object, which is what this equation is saying right here. And this kind of explanation is something that AP is really, really big on. It's really cool if you just have this equation memorized, but really, you got to think about what is it trying to say. So if I put a force on something, that's why there's an F there. If I put a force on something, then I will change its momentum, which is why we have delta P on the other side, right? Also, just the same. So we learned in the momentum unit, when you apply a force, you change the momentum, and it's the same thing over here. When a torque is applied to an object or system, it changes the angular momentum of that object. We just add that word angular because now we're talking about things moving in a circle, but it's the same idea. If you apply a force or you apply a torque, then you're going to change the momentum of that object. Torque just means it's going to start moving in a circle. Okay, there is one extra equation, and there's this equation, L equals I omega. There's that equation to get angular momentum. Remember, angular and rotational just mean the same. They're the same thing. So there's two ways to calculate this L, and you could do I omega, or you could also do MVR. If you notice, though, we have M times V, which is just P. So you could go from regular momentum to circular momentum just by multiplying by R. And we've seen that same relationship happen with velocity and acceleration. If you just multiply the regular by R, how far you are from the center, just take your regular thing, multiply by how far you are from the center, and that's how you change from regular to circular. It does help. I like this equation because it does help explain the units for angular momentum. Remember, P, the units for regular momentum, P is kilogram meters per second. That's just mass times velocity, right? Mass, that's kilograms. Velocity is meters per second. So here's kilograms times meters per second. That's velocity. So kilogram meters per second is for momentum. And then this equation just takes that and multiplies by R. And R is a distance, right? How far are you from the center? And so because it's a distance, that unit is M. And that means you're just going to take kilogram meters per second, multiply by another M, another meters, and the units for angular momentum, those are kilogram meters squared per second. Okay, kilogram meters squared per second. Those are the units for angular momentum. Okay, I want to explain moment of inertia a little bit better. Talked about it a little bit last week. I didn't want to give you all the details all at once because it's a little bit, it's just weird. I don't know. I don't know how to explain that. I know that when I was going through learning it, just moment of inertia was just weirded me out trying to learn it. It's really not too bad though, and hopefully I can help to make it a little bit more clear if it hasn't been clear for you already. So I want to start out by looking at some review. Remember that inertia is a measure for how much an object will resist a change in motion. So let's think of, like, say, a Mazda 3, that's what Mr. Christopher drives, remember, and a Ford F-350 truck are both sitting still. You push on each one with equal force to try and make them move. Which one? So you're pushing on both, equal force. Which one is going to resist your push more, the Mazda or the Ford F1 or the Ford F-350? It's the F-350. Why is that? And that's just because it has more mass. And so more mass equals more inertia. So the more mass you have, the more you will resist being pushed, right? So if you look at the moment of inertia equations, I think it was on page 211, something like that. 210, sorry, 210. Let's change that really quick. Let's change that. That is 210. Okay. And I'm going to put them up, a couple of them up right here anyway. There is a pattern. They're all a little bit different, but there is a pattern. What do you notice is in every single one of these things? There's an M. M in the first one, this is a rod spinning at its end. And then the second one, picture here, is a sphere or a ball that's spinning. And that also has an M in it. And then this last one is like a metal hoop that's standing on its curved side and spinning that way. And what do you notice is in this one too, just like the first two, it also has an M. They all have an M, which makes sense. If we're measuring inertia with these equations, they should have mass in it because more mass means more inertia. So that should make sense. But what I also want you to notice is that they also have the mass multiplied by some length squared. Like with the rod, you take the length in the rod, and that's L squared. That's in there. If you look at the ball, we have R squared. R is measuring a length. It's measuring from the center out to the edge of the ball. That's a length, and it's R squared. And then even if you look at the third one with this hoop, we're adding two things up, right? But if we look at both pieces, this first one has an R squared, and that's a distance from the center out to the side. So, and then we also have this W squared for width. So how wide is your hoop? That's still measuring a length, right? That's still measuring a distance. How far is it across that hoop? And look, just like all the other ones, it's also squared, okay? So even though the equations are all a little bit different, what is really important to see is the pattern. They all have mass times some kind of length measurement squared, okay? And so that should help us understand where the units for I then are always going to be kilogram meters squared. So it doesn't matter what shape you got, it doesn't matter which way it's spinning, your moment of inertia, your I, will always have the same units, kilogram meters squared. I already mentioned this. Still more mass means more inertia, so there's no surprise there. That's something we should already know. Something AP does want you to know is that the length also matters. And we've just been talking about that. Length goes into all of them. So the moment of inertia increases if the that should be an F. If you have more inertia if your mass is farther from the center. So if you take your mass and you spread it out farther, you're going to have more inertia. Okay, so exploring rotational inertia and momentum a little bit more. So really trying to break this down a whole bunch to really make sure we got the details. So we just said the mass being farther from the center of the rotation matters. If the mass is farther from the center, you have more inertia, at least more rotational inertia. And so think of two kickballs. That's what we need to imagine here. Think of two kickballs. Each kickball is tied to their own string. The string for the first ball is only 1 foot long, and the string for the other one is 10 feet long. So you stand in one spot and use the free end of the string, right? The end of the string that's not tied to the ball, the other end, to spin each kickball. And you're standing at the very center of the circle. So you're right in the middle. And so the one tied to the 10-meter string will have more rotational inertia than the one that's on the 1-meter string because its rotational motion has a larger radius, right? Bigger radius. We saw in the other equations. R matters. It's part of the equation. If you make the radius bigger, then you have a bigger I. You have more inertia. Okay, so that's kind of a super simple version of it because we just have a ball and we're talking about, well, how far is the ball from the center? But it's a little bit deeper than that. It's not only does the radius matter, and we know that the radius matters, we know that the total mass matters, but how that mass is spread out also matters. So I want you to think of a CD. I've got a couple pictures here. Think of a CD. Like, you go to the store and you actually buy music instead of just listening to it on YouTube. I know, I'm like really old fashioned. Mr. Christopher, get out of here. You're old. Nobody buys CDs anymore. We just listen to our music on the internet and stream, whatever. CDs are still a thing. Plenty of people buy them. Hopefully you at least know what a CD is. If not, here's a picture of it. Okay, here's a CD. And now I also want you to imagine a metal hoop, kind of like this other picture. This is just a copper wire made into a circle. Okay, and so what we want to do is pretend that let's say this CD and this metal hoop are the same size. From the center out to the edge, the far edge, they're the same size. So they have the same radius, and let's say they have the same mass too. If the CD is 0.1 kilograms, the hoop is also 0.1 kilograms. So same M, same mass, and same R for the same radius. What's different about these things? They should have the same inertia, right? Same M, same R, but they don't. The metal hoop has more rotational inertia than the CD because all of the mass is at the edge for the hoop, right? There's nothing in the middle. all of the mass is right on the edge. Whereas the CD is different than that, right? It's got plenty of mass that's spread out closer to the center. The CD is not just a ring, it's a disc. It's a disc. And so not all of the mass is at the edge. Some of the mass is towards the middle, some of the mass is in between, right? And so if you look at the hoop, because all of the mass is at the edge instead of spread out evenly in the middle, it has more rotational inertia. So they have the same mass, they have the same radius, but the CD's mass is more spread out towards the center, whereas the hoop, it's all at the edge. And so that matters too. And the hoop has more rotational inertia because it's all at the edge. One quick thing I want to remind you about momentum. So did a whole lot of talking about inertia up here. I want to bring it back to momentum. When we did our momentum unit, we talked about how momentum is conserved, right? So the momentum at the beginning and the momentum at the end, those are equal. It does not change unless there's an outside force applied. Guess what? Angular momentum is conserved too. Okay, so it's a lot of the problems are going to feel a little bit similar to those. We did some pretty complicated ones with the inelastic collisions. We won't have anything really like that. But it's the same idea that momentum you have at the beginning and the momentum that you have at the end are the same. They're equal. You can literally put the beginning equals the end for momentum. Okay, so we're going to do a figure skating example to kind of tie this all together. And the example actually kind of does work kind of nicely as an example for your book problems. So let's dig in. When a figure skater goes into a spin, they often start looking like picture number 1, right? Her arms are out, one of her legs are out, and as they start the spin, this is what she looks like. And then they tuck in, kind of like picture number 2, bring their arms in tight, and what happens usually? They start to spin faster. I don't know if anybody watches figure skating or pays attention to that event in the Olympics, but a lot of them do this. They use this technique. When they start a spin, they have their arms spread out, and then they tuck them in. So if we ignore friction, that means there's no outside forces, and so the angular momentum will not change. Okay, so the angular momentum is constant. Whatever momentum she has in picture 1, it's the same momentum that she has in picture 2. Well, which picture has more rotational inertia? Kind of like comparing the CD to the hoop, picture 1 has more rotational inertia because her mass is spread out over a bigger radius. She's got her arms out, she's using more space, spreading her mass out. And then in picture 2, she brings all of her mass in close to the center. And so her inertia in picture 2 is smaller than in picture 1. So now let's go ahead and actually do a problem with this, like with numbers and stuff, so that kind of help you out and give you that example. Let's say in picture 1, her rotational inertia is 8 kilogram meters squared, and she is spinning at a rate of 1.7 radians per second. Remember, anytime we do these problems, we want radians, not revolutions. How fast is she going in picture 2 if her rotational inertia is now 5.2 kilogram meters squared? So in picture 1, her rotational inertia is 8. In picture 2, her rotational inertia has gone down to 5.2. I want to point out something really quick here. Rotational inertia, that's the same thing as moment of inertia. You should want to be able to go back and forth that those mean the same thing, because your book will use the words moment of inertia and AP uses the words rotational inertia. Those are the same thing. Okay, so I don't want you to be getting mixed up. Those are the same thing. Okay, so the first thing, here's what we're going to do. We know her rotational inertia, and we know how fast she's spinning, and so we're just going to multiply those, and we know I and we know omega, so we can calculate her momentum pretty easily. Just multiply those two, 8 times 1.7 to get her rotational momentum. 8 times 1.7, when you do that, you get 13.6. And the units for angular momentum, as we talked about before, kilogram meters squared per second. So I know how much momentum she has in picture 1. But what was the big idea that we learned about momentum? It's conserved. So in picture 1, if her momentum is 13.6, well, guess what? In picture 2, her momentum is still 13.6. And so we're still going to use the same exact equation. Okay, same exact equation. We know that L is 13.6. And we also know that her the rotational inertia in picture 2, is 5.2. And so we're just going to take those numbers and plug them in. L is 13.6. We just figured that out. They told us in the problem that her I for picture 2 is 5.2, and we want to know how fast she's spinning. So that's our omega. And we just one algebra step to solve. Now we've plugged in just one algebra step to solve it. Omega is 13.6 divided by 5.2. When you do that, you get 2.62 radians per second. Okay, so the big idea is that her momentum did not change. We were able to calculate her momentum using the information from picture 1, and then we use picture 2 and the momentum to figure out how fast she's going. Okay, so I know that this example seemed pretty quick, pretty straightforward. I want to give you some tips and tricks not to fall for. Do not fall for these tricks. I'm trying to help you avoid getting tripped up right now. Kind of like last time with the torque equation, the equation that we learned today, L equals I omega, is simple looking enough, right? But just like last week, the I and the W might need a little bit of work before you can jump into the L equation, okay? I want to remind you that if there are multiple pieces to your system, then the I you should be using is the total rotational inertia. So all you got to do that is figure out I for each piece and then add them up. And when you add them up and get the total is what goes into this equation, okay? If there's a piece of the system at the center of the circle, then I is 0 for that piece, because remember that everything is like an mr squared, and if you're standing at the center of the circle, well, then r is 0. You don't have any distance to the center because you're at the center. And so that for that piece, I'm not saying the whole thing, just if there's a piece that's at the center, then for just that piece, I is 0 when it's at the center. I know I mentioned this in the example that I did, but just to say it again, rotational velocity measurements must be in radians per second. And as a reminder, to change from revolutions to radians, just multiply by 2 pi, right? Because one time around the circle, that's what a revolution is. One time around a circle is 2 pi radians. You might have to, I think a couple of problems, you have to use the definition of angular velocity. So they give you a distance like 3 revolutions, and they give you a time like 2 seconds. And so you have to do 3 divided by 2 to get your omega. Again, remember that you cannot, with this equation, you cannot use it in revolutions per second. It has to be in radians per second. So just keep that in mind. These are just a couple of things that are really easy to get tricked on. And I don't want you to get tricked on them. So take note of them. Okay. All right. And that is the end there for us. No news, like I said, no new stuff coming out. We'll be pushing out some kind of practice test next week. I'm not 100% sure how long that's going to look like right now. I'm kind of, this kind of thing has never happened before, so we are trying to figure things out as we go. I'm just trying to do the best I can for you guys. Okay. So that some kind of practice test, AP style, coming out next week. Nothing new. Okay. Just another reminder as well, be looking on Google Classroom for a survey about times that will or will not work for you as far as doing a Zoom review or a review on Google Meets, something like that. That'll be coming out, so make sure you answer that survey so that we can get some kind of review set up. You guys can ask some questions. All right, I'm done for this one. All taken care of. Hope you guys are staying well, stay positive, take care, and talk to you soon.